Hi everybody and welcome back to Gaffy's Grinds. This is the channel where we take concepts from junior cycle science, we break them down into small manageable chunks, and we give you guys lots of practice to do to make sure we get the information to go to our long-term memories. This is our second video on our module on electricity. Now before we begin, the usual warnings guys that we want to eliminate all distractions, so please turn your phone off now. Or put it in another room or put it on do not disturb so that you don't get notifications. Notifications are the number one reason why we get distracted and we go off and do something else instead of focusing on our learning. The second thing and the most important thing is any tasks, activities I ask you to do during these videos, really important that you do them. The videos are designed to make sure you get enough practice to make sure the information goes to your long-term memory. If you don't do the practice, then that's not going to happen. And that means you're pretty much wasting your time. So we don't want that, okay? You're committed enough to come and watch the videos. Let's make sure that we get the most out of it by committing stuff to long-term memory. Now, this section's video is going to be about 3 particular concepts to do with electricity, and they're really, really important. Without understanding these, you cannot understand anything to do with electricity, really. So the 3 things we're going to be learning about today are current, something called potential difference, and resistance. Before we begin, we're going to do a quick recap of our previous lesson. So you should have already watched lesson 1 before you do this. If you haven't watched lesson 1, you need to go back and watch it first. Otherwise, this is going to be very difficult. Okay, so we're going to begin by answering 4 questions about the previous lesson's learning. Okay, so what I want you to do is I want you to answer these wherever you're doing your questions. If you've got a revision copy or a practice copy, you should get that out now and do these questions, please. Full sentence answers, ideally. So pause the video and don't play it again until you've tried your best to answer these 4 questions. Great, so hopefully now you have answered your 4 questions and we are ready to continue. I'm not going to spend too much time going through these because you should be pretty familiar with this stuff already. So I'm just going to throw up the answers here. These are the answers. Again, pause the video to make any corrections that you need to now. Okay, so the very last question there might have been the most difficult one. How do we count electrons? Well, we know that numbers of electrons, we have billions and billions of electrons in any piece of material, any piece of metal or any piece of wire. So we have this word Coulomb, which is a certain amount of electrons. It's 6 quintillion, and so we can count in Coulomb. So every time you have an extra Coulomb, you're adding 6 quintillion electrons. It just makes it easier than writing down all those zeros after to make up quintillions. So that was probably the only one that was reasonably difficult there. All right, so if you didn't get those guys and you're not sure that doesn't make sense to you, you really need to go back and watch video 1 again. Okay, right, on to today's lesson. Okay, so we are of course talking about electricity. And in the first lesson, we learned some of the things that are required for electricity. First of all, we need charged particles. Now, in electricity, we're talking about a specific type of particle flowing, and that is the electron. But any charged particle can technically carry an electric current, but usually we're referring to electrons. Now, metals are examples of materials that have these electrons. Now, all materials have electrons, but there's something special about metal. So first of all, we need to have, and these E minuses are negatively charged electrons because electrons have a negative charge. Okay. The special thing about metals, though, is they have delocalized or free electrons, which allows them to move around. They're not stuck to one particular atom. They're able to move around. So they have a freedom of movement. Now, this is not all we need for electricity, though. In this case, we do have charged particles, as you can see. So is charge there? Yeah, we have negatively charged. Electrons. But this is what we call an open wire. So imagine you've got a wire, a piece of metal, or a piece of metal wire, and it's just straightened out. So you've got this like a guitar string would be. So straightened out. It's not looped. So the options here are straight or looped. Okay, so this is an open wire. This is straight. When the wire is like this, we don't get a flow of electrons. So flow would refer to all the electrons start to move in the same direction. So in an open wire, this does not happen. So this is not, we do not have electricity here. So something that we need for electricity to occur is we need our charged particles like we have in an electron. They have to be free to move just like they were in the one above. But this time they are in a closed loop like this, a closed loop. Okay, and when they're in a closed loop, we call them an electric circuit. Now, when this is the case, the electrons can move in the same direction, like this. So they will all start to flow around the closed loop. So now we have particles which are charged, which is what we're interested in. So charged, yes, they are. We have these charged electrons, yeah. And they are able to flow. So they are charged and they can flow. Now, so we have the conditions necessary to generate an electric current. We're not quite there yet though. The final ingredient for an electrical circuit, the final ingredient I should say, is a power supply. So we have this closed loop like this. We have a loop, we have this loop of wire. So this is a metal wire. But to get the electrons to flow, we need what we call a power supply. And the power supply is essentially able to push the electrons around the circuit. So we've got these electrons, and when the power supply, when they are in a closed loop and the power supply is turned on, the electrons will then start to flow. Okay, so like this. They will now flow when the power supply is switched on. Like that. Okay, so the power supply pushes the electrons around the circuit, and this is going to allow them to transfer energy. Now, if we were to take this circuit at any particular point, say we were to take a look at what's going on here, zoom in on the circuit, what we would have if we zoomed in, I'm just going to zoom in and make this straight piece of wire like this. Okay. What we would have is we would have all of these electrons like this. And once the circuit is all connected up and is connected to the power supply, the electrons will start to move, and we'll say they're moving from left to right here. So I'm showing them moving all towards the right. So the electrons start to move in the wire like this. Okay. Now, when the electrons pass a certain point in the circuit, so say we wanted to measure how quickly the electrons pass this point. All right. So say the point is the edge of the screen here. So the edge of the screen over here. All right. Say that edge of the screen there. We want to measure how quickly are the electrons going past that particular point. Now, how do we measure electrons? Remember, we don't count electrons singly. We count them in coulombs. So in 6 quintillion of electrons at a time. That's how we count them. So we count them in coulombs. Now, if we were to take this point at the edge of the screen, like I highlighted, and we were to count how many electrons are passing that point in a certain amount of time. So say we were to say in 1 second, how many electrons pass there. So say as they move across from right to left there, as you can see, in that amount of time, 4 electrons that I've drawn here have passed it. So say that was going quite slow. There's 4 electrons. have passed in that particular amount of time. Now let's imagine for a second that each of those electrons actually represents a coulomb of electrons. And 4 coulombs of electrons have passed that point in that particular amount of time. So what is the particular amount of time? Well, the particular amount of time that we measure coulombs of electrons in is we use the amount that pass in 1 second. So say coulombs, sorry, spell it right, C-O-U, even I keep making that mistake, coulombs per second. Okay, so if we were to count the number, we would count the number of coulombs every second. Okay, so say in 1 second, so I'm just counting to myself from 0, 0, 1. Okay, so at this point, I have about 2, and I had these 2 here, and I had about half of this one. Just a rough guess. So that's 2.5 coulombs in a second passed. So that would be one speed of electrons flowing, if you like. What if the electrons were flowing much more quickly and I started counting again to 1 second? So 1. Okay, so in that case, that was still 1 second, but much more electrons passed that time. So it went from here. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This time, 11, 12. That is a much faster flow of electrons. So you've got 12 coulombs of electrons in 1 second that time. Okay, now of course we can't see electrons, so we don't really count them like this by looking at them. We would measure them in a different way, but that's essentially what we're doing, measuring how quickly the coulombs are flowing. Okay, so how quickly the coulombs of electrons are flowing in a circuit or through a circuit. We have a word for this. So how quickly the coulombs of electrons are flowing through a circuit. That's what we're measuring in this case. How quickly the coulombs of electrons are flowing through a circuit. This is what we call the current. The current. So current, for example, in a river is how quickly the water is flowing. So you could measure this by picking a point on the river and measuring how much water passes that, how many liters pass it in a given amount of time. So your time might be in a minute or it might be a second, however much you decide. If you can find out how many liters flow past that per second, you can get the current in the river. Of course, we don't often measure that. We usually just look at it and we have an idea how quick is the current. But we can't really do that for electricity because you can't see the electrons flowing like we can water. But it's the same idea. So how quickly the coulombs of electrons are flowing through a circuit, that is the current. Now, current gets the symbol capital I. So the unit symbol for current is a capital I. Now, why is it not capital C, you're saying? You're going, why the hell have they used I? Well, C is already taken, so I is used for current. Now, current is measured in a unit. So we always have a number. We're measuring how much a current is. We've got to put a number on it. So it could be 1 coulomb. Remember, we're measuring coulombs per second. So say if we have 1 coulomb in 1 second, 1 coulomb in 1 second, or a coulomb per second, 1 coulomb per second, or 1 coulomb in 1 second. That's equivalent to the unit 1 amp. So you might have heard of amps before, and 1 amp is the same as 1 coulomb every second. Okay, that's what an amp is. It means 1 coulomb is flowing in a circuit past a certain point every second, 1 coulomb of electrons. So amps are what we measure current in. So current is measured in amps. What if we had 2 coulombs in 1 second? 2 coulombs in 1 second. What would I say about the amps? So on 3, I want you to tell me, what do you think, how many amps is that? 2 coulombs in 1 second. 1, 2, 3. Speak it to the screen, sorry. You should say it in 1, 2, 3. Okay, I'm hoping that you see that if 1 amp is 1 coulomb every second, and we have 2 coulombs every second, then this is 2 amps. Now, again, to shorten the word amps, now amps is pretty short already, so we don't, you know the way we have, instead of kilogram, we have a unit symbol of kg. So notice the difference. This is a unit symbol because kilogram is a unit. This is a quantity symbol because current is a quantity. Okay, so just not to mix them up. So unit symbol for kilogram is kg. The unit symbol for amps, can you guess what it is? Yeah, I'm hoping that you realize that it's going to be A. So amps. So you could write 1A there, or you could write 2A here, 2 amps. So current is I, amps is A. We have to be able to distinguish between them. Right, I'm going to get you to do one now. What if I had 12 coulombs flowing past in every 1 second? So 12 coulombs in 1 second. What would the amps be there? Please speak your answer to the screen now. 1, 2, 3. Okay, we would have 12 amps. All right, maybe do one more. Okay, what if we had, this one's I'm going to make it a little bit harder now. What if we had 30 coulombs in 5 seconds? So have a think about that one. What would we need to do there to find out how many amps we have? Okay, so speak your answer to the screen now if you think you can figure that out. If not, you might need to pause the video, do it on a calculator or write it down on a bit of paper. Do that now if you need time to pause the video. Okay, well, the key thing here is it's coulombs per 1 second. So to make this 1 second down here, what would we do to it? We would divide it by 5 to make it from 5 seconds to 1 second. So if we divided this by 5, we need to divide this by 5. So we're going to get 30 coulombs in 5 seconds is the same as 6 coulombs in 1 second. Now, if we have 6 coulombs in 1 second, then we have 6 amps, or 6A. Good. All right. It's time now to do some more questions. Okay. So what I'm going to do is we are going to have a go at these questions now, please. Okay. So I'm going to get you to do these in your practice copy underneath where you did the last ones. Now, the first questions were 1 to 4. These are 1 to 6. If you want to continue on the numbers and say that this is 5 instead of back to 1 again, you continue doing that. That's no problem if you want to keep them in order. If not, then you can just go 1 to 5 again or 1 to 6 again here. Okay. So pause the video, please, and do these questions now. Okay. So this is now your answers. So let's pause the video and check them. I don't think any of them should cause any real problems. Okay, they're pretty straightforward. If you need to make any corrections, so we should either be ticking them correct now, or we should be fixing them. Okay, so if you need to make any corrections, you should pause the video and do that now. Okay, now. Okay, so you have learned about current. Now we're going to go back over here and we are going to talk about how electrical circuits transfer energy. So when we learned about energy before, we learned about something called energy stores and energy transfers. And we learned that electrical working was a type of energy transfer. Now, electrical working happens in electrical circuits. So as you can see from this piece of text here at the top of the screen, electrical circuits can transfer energy from the power supply to the surroundings. So if we draw this diagram again, we have our power supply. I'm just going to actually make that a bit smaller. I'm going to run out of space here. Oh, sorry. Okay, apologies about that. Now we have our power supply. And the whole idea here is that the power supply, if it's connected around by a wire, that means that the current is going to flow. And the reason why the electrons start to flow, oh, don't want that, don't want to do that. We've got our electrons in the wire here. Is that the power supply supplies energy to the electrons. So if we were to take this particular electron, it's just been in through the power store. Remember, the electrons are moving. We'll say they're moving in a clockwise direction here, like that. So they're moving around this way. There we go. So the electrons are moving this way. That means that when an electron is here, it has just been past the power supply. And if it's been to the power supply, then energy has been transferred to the electron. So if we look at its energy store, we would say the energy store of these electrons, which have just been past the power supply, is pretty high. So what's going on inside the power supply? Well, generally, inside the power supply, there's energy being released, either through chemical reactions or directly from the mains, but energy is being passed or transferred to the electrons. Now, by the time the electrons get back around here, the idea is, well, basically, as it goes along, energy can be released from inside the circuit where it's been stored by the electrons. Energy can be transferred. And that's the whole point of an electric circuit is to be able to transfer energy from the power supply to the surroundings. Now we'll talk about how that happens later on, but know that energy has to be transferred to the surroundings. Otherwise, there's no point in just having electrons going around and around in a loop. That's no good to nobody. The whole idea of electricity is it's able to transfer energy. Now, if energy is being transferred, where is it going? It's going to what we call the surroundings, which is just the area around the circuit, outside the circuit. So if you think of the electrons as inside the circuit, everything outside of the circuit is the surroundings. By the time it gets back around here, then the energy has been reduced because energy has been transferred out of the electrons' energy store. So the energy store has now emptied quite a bit. Energy store. Okay, so the energy store is now much lower in energy. Now, let's talk about the types of power supply then. So the power supply is what gives the energy to the electrons to help them move. Okay, so there are two main types of power supply that we are going to look at. So the first one, so we've got power supply. Okay, so first of all, what is a power supply? A power supply is what transfers energy to electrons in a circuit. A circuit. That is what a power supply is. It's what transfers energy to electrons in a circuit. There are two types of power supply. Type number 1 is what we call mains. Mains. Now the mains comes from the national grid. It's basically the sockets that you plug into in your house. Wires are carrying electricity, which is electrons with lots of energy, are carrying them to your house, to the mains. Now mains isn't always available, okay? So sometimes we can have a second type of power supply, and that is what we call a cell. Sorry, where are you going? We've got cell. So we've got mains and we've got cells. These are the two types of power supplies. So what I want you to do is ignore the writing at the top of the screen for a second, just where I have, just what I have drawn there. I want you to take down in your practice copies, what is a power supply? And then the types I have covered up. I want you to complete the diagram as far as I have done there, basically from memory without rewinding it back. Okay, so pause the video, do that now, please. Okay, so you should have written that the power supply is what transfers energy to electrons in the circuit, and the types, you weren't able to see them, but this is what you should have. We have mains and we have cells. Now we need to talk a little bit more about cells. I think people get the idea of what the mains is. It's what you plug in, your plugs in the house into, and electricity is carried into your house by the national grid, which is wires that come from power plants, bring electricity to your house. But cells are basically devices, and they are devices that have a large amount of energy in what we call the chemical energy store. So there is a large amount of energy in the chemical energy store, and this energy can be released by doing chemical reactions. So that's what a cell is. A cell is a device which has lots of energy in its chemical energy store. And that energy can be released. That can be released by chemical, that can be released by chemical reactions. So basically, cells do chemical reactions which release energy, which can be then transferred to electrons as they pass. That's what a cell is. It's a device that which lots of energy in its chemical energy store, and it can be released by chemical reactions, that should say. Sorry, by chemical reactions. So that is a cell. Now, some people confuse batteries with cells. Quite a lot of people do this, actually, a battery and a cell. Now, they are similar things, but a cell, that's what this is, a device that has lots of energy in its chemical energy store, and it can be released by chemical reactions. A battery, then, is similar because it is made of cells. So a battery, actually, I'm just going to put that a bit further over here so it doesn't clog it up. A battery is basically a device then which is made of two or more cells. So it's made of cells. So batteries are made of cells. So a battery themselves is two cells or more. A cell, though, is a special device which has lots of energy in its chemical energy store that can be released by chemical reactions. You put a few cells together, you make a battery. Okay. Now, I'm going to go back up and just take a look at this diagram again. We said that the power supply supplies energy to the electrons or transfers energy to the electrons which move around in the circuit. We then said energy can be transferred from the inside of the circuit, so from the electrons to the surroundings. And the question is, How much energy can be transferred? So how much? That's a good question. Well, how much energy can be transferred? So if we talk about the amount of energy that can be transferred, the amount of energy that each coulomb of electrons transfers. So every coulomb going past will transfer energy, and the amount of energy that each coulomb of electrons transfers this is what we refer to as the potential difference. Potential difference. So the potential difference is the amount of energy that each coulomb of electrons transfers. This is also known sometimes as the word voltage. The voltage. So the voltage of the circuit is the amount of energy transferred by each coulomb of electrons. It's called the voltage because we measure potential difference in volts. So measured in volts. Okay, so voltage or potential difference is measured in volts. The key thing to remember is that if you have a high potential difference, that means that a lot of energy is transferred for every coulomb. So a high potential difference means a lot of energy is transferred by each coulomb. Now, if the electrons, the coulombs of electrons, have a lot of energy, that means that they are going to be flowing quickly because they have more energy. So if they are flowing quickly, then you have a higher current, because current measures how quickly the electrons or the coulombs of electrons are flowing. So high potential difference or high voltage means you've got a high amount of energy transferred, and if you've got a high amount of energy being transferred, then you've got a high current because the electrons have a lot more energy. So what would happen then if I have a low potential difference? Low potential difference. Well, if I have a low potential difference, then I'm going to have less energy transferred. And if I have less energy being transferred by each coulomb, they're carrying less energy, then they're going to go slower. And that means we're going to have a lower current. Okay, so they do have knock-on effects. Okay, so just to recap, the potential difference is the amount of energy that each coulomb of electrons transfers. The potential difference, or the voltage, is supplied by the power supply. So power supplies can be either mains or cells, and these transfer energy to the electrons' energy store. When the electrons have more energy, they're going to move faster, so the current will be faster, and they will transfer more energy. When the power supply doesn't transfer as much energy, then the electrons are carrying less energy, the current is going to be lower. Okay, so they're the patterns you're looking for. High amount of energy, fast electrons. Low amount of energy, slower electrons. The power supply is what provides the energy. And the key here is that we want to transfer energy from the power supply inside the circuit to the surroundings. The next little set of things is going to talk about how does that transfer happen. Voltage or potential difference is measured in volts. So higher amount of voltage means more energy is being transferred and a higher current. Right, time to do some more questions now. Here we go. So the first question says, name the two most common power supplies. You should be able to do that, no problem. So I'm just having a quick look through these. I think you should be able to do those, no problem. Yeah, okay, so they should be pretty easy. We've done all of that. There's nothing there I forgot to do. So pause the video and try to do those questions now, please. Okay, so well done as usual. Now you should only be watching the video if you have tried to do all the questions, and here are your answers coming up. Don't forget to pause to make any corrections that you need to. Okay, so the most common power supplies are mains and cells. The difference between a cell versus a battery: cell is a device that has a lot of energy in its chemical energy store, and it can be released by a chemical reaction. The difference is a battery is just a device with at least 2 cells. So a battery is more than 1 cell, but a cell itself is the magical bit. That's what stores the energy in its chemical store. What is potential difference? It's the amount of energy each coulomb of electrons can transfer. Potential difference then is measured in volts. Why are metals good conductors of electricity? They're good conductors because they have free electrons, or their electrons are free to move. That's a key thing. They have to be able to flow. If you've got a material that the electrons can't flow in, then electricity will not be conducted or will not work. So if it's a conductor, that means electrons are free to move in it. Next one, what is 1 amp? 1 amp means 1 coulomb of charge per second passes a point in a circuit. So 1 amp means 1 coulomb of electrons pass every second. What do we count? How do we count electrons? We count electrons in coulombs. And why do we not count them by number? Well, obviously the numbers are too big. So we don't count them by number because the numbers are far too big to deal with. So we use coulombs. Right, last little bit, guys. Okay, we are going to be looking at how energy gets transferred out of the circuit. Okay, so that's what we should do now. So we're going to take a look at our power supply again. We're going to draw our power supply. So we've got our power supply here. This is our power supply. What part of the, what quantity or thing comes from the power supply, guys? So on 3, 1, 2, 3. So power supply supplies the voltage. It transfers the potential difference. It transfers energy to the electrons. So power supply supplies the voltage. We then need a conducting wire, which has electrons which are free to move. And it needs to be in a loop. So we're getting to now the stage where we have all the things we need for a circuit. So we've got an electric circuit now. Okay. We've got our electrons, and they are, which are our charged particles, remember, negatively charged particles, our electrons, and they have energy and they are moving around in the circuit. So the power supply is supplying energy to these electrons. Okay, and they are moving around the circuit like this. And we know that if we look at this electron, the energy store is full because it's been just through the battery or through the power supply. So it's full of chemical energy, or the chemical energy store. And if we look at this one, it's just been around the circuit. It is empty, or it's less full. So here's the chemical energy store now. So there is less energy there now. So where's the energy gone? Well, obviously there's no point in energy just being transferred within the circuit. It'll just go around and around. It has to be able to get out of the circuit. That's why they're useful. We use circuits because they can transfer energy out of the circuit. Now we do this by putting what we call a device into the circuit. So a device is a object which is able to transfer energy from inside the circuit to outside of the circuit. So this is what we call an electrical device. D-E-V-I-C-E. An example of a device could be something like an electric heater. An electric heater. So when we plug an electrical heater in, we put the device, which is the electric heater, we put it into the circuit. We join it to the circuit. And it's the electric heater is the device which is then able to take the energy which is moving around inside the circuit. The electrons are carrying around this energy. It's able to take the energy and convert it or transfer. Energy gets transferred to the surroundings and you get warm. So energy is transferred to the surroundings. Remember, where are the surroundings? The surroundings is outside the circuit. Surroundings are outside the circuit. Now, so circuits do this by having electrical devices in them. Like other examples of devices are things like lamps or things like motors. These are other types of devices which we can put into a circuit, and we can transfer energy from inside the circuit to outside of the circuit. How do they work? Well, if we zoom in on the wire here, so I am zooming in on the wire. Damn, stop doing that. Okay, so here I have this string of electrons flowing from left to right in my wire. And in a normal wire, they are free to flow along. Okay. So the way a device works is a device will have a way of getting the electrons to slow down. So there'll be points in the wire inside of the device, like this, where the electrons aren't as easily able to move. And when the electrons encounter this, what happens to them is when they try to squeeze through here, through this gap, they get really slowed down. So basically, we're slowing down the flow of electrons in the circuit. Now, obviously, they will keep flowing. They will eventually get through, but they will slow down. And when they slow down in this section here, because they slow, they have less energy. And when they do this, the less energy, where does the other energy go? Well, the energy gets transferred to the surroundings. So by slowing down the electrons, energy gets transferred to the surroundings. So because the electrons move slow, the energy gets transferred to the surroundings. And this here is known as resistance. So where electrons struggle to flow or get slowed down, we call it resistance. Okay, so what is resistance? As we can see here in the box, resistance is how electrons can be slowed down in the circuit. Resistance has the symbol or, capital or. So we have three symbols now. We have V for voltage, or V for potential difference. We have I for current. And lastly, we have or for resistance. So we have V for potential difference or voltage, I for current, and or for resistance. So resistance is how electrons can be slowed down by the circuit. And we use the unit of ohms to measure it, ohms. So you might have 5 ohms, you might have 10 ohms. And the unit symbol is this Greek letter called omega. Omega. It's kind of like a horseshoe shape. So I'll just draw it again. It's like over, then a loop like that, and then over. Okay. It's kind of like a horseshoe lake or an oxbow lake, I think they're called in geography. It's kind of a bit like that. It's the Greek letter omega, and we use it for ohms. So ohms, basically, more ohms, so 10 ohms versus 100 ohms. 100 ohms is obviously a bigger resistance. And that means that the current or the flow, the electrons are slowed down more. So higher current or higher resistance means slower electrons. Electron speed, if you like. Or another way of saying this, current. Okay, so higher resistance, lower current, because you're slowing the flow of electrons down. All right, so it's time now to do some practice on this last little bit. Okay, so last few questions. Okay, number 1, what is resistance? Number 2, in an electrical device, what happens to the electrons? Number 3, why do we use circuits? Number 4. Okay, I'm thinking you should be able to answer all of those. So what I want you to do now is pause the video and have a go at all of them for me, please. Okay, so the answers are coming up now. First of all, what is resistance? Resistance is how electrons can be slowed down by a circuit. So that's the definition. Resistance is how electrons can be slowed down by a circuit. So that's a full sentence answer. It's a good one. In an electrical device, what happens to the electrons? So inside a device, all devices have this. They slow down the electrons. So in an electrical device, the electrons are slowed down. So there's a resistance. So all devices have a resistance, or so provide a resistance. How do we use circuits? What do we use them for? We use circuits to transfer energy to the surroundings. So we take energy from inside the circuit and put it to outside the circuit. It might be light, it might be heat, it might be sound, it might be a combination of all of them things, but we're trying to transfer energy to the surroundings. When electrons slow down, they lose energy. Where does that energy go? The energy is transferred to the surroundings. A circuit has very high potential difference. In other words, has a very high voltage. Oops. Sorry about that now. Has a very high potential difference, means voltage. Do you think it will have a high or a low current? Explain your answer. So we've got number 5, high or low current. So high potential difference, it means the electrons have a lot of energy. So if you didn't know the answer to this, after telling you, if I have a high potential difference, the electrons have a lot of energy. So do you think we'll have a high current or a low current? So the key here is high potential difference, which means high amount of energy. That means you've got a high current because the electrons are moving fast. Okay, so why is the current higher? Electrons have more energy. They have more energy, they're going to move faster. Same as anything that has more energy. Anything with more energy will always move faster. Damn. Energy. Now, what about the last one? If a circuit has high resistance, how do you think that would affect the current? So this was 6, 5, and 6, 7, and 8. So high resistance, how do you think it would affect the current? So high resistance. Now think about what the resistance does to the electrons. What does it do to the electrons? Slows electrons down. So how do you think it would affect the current? High resistance, what would it say about the current? If you weren't able to write it down, maybe you can now after I've given you that clue. Okay, high resistance should be low current. Explain your answer. Why? Well, the resistance slows down the electrons. Slows the electrons, which means the current is going to be lower if the electrons are moving slower. All right, guys, that was 3 really important concepts: current, potential difference, and resistance. You must understand them 3 things in order to get electricity. So if you're not, I'm hoping that you're pretty sure of what the differences are between them. If you need to check them again and maybe make a note of them so that you can test yourself and quiz yourself, there is the definition for potential difference. Okay, if you want to pause the video and write that down and you can get practice in it, that is the definition for potential difference or voltage. For current, it's here. There is the definition for current. If you need to write it down, get practice in it, make sure you can recall it. And lastly, so you should have paused the video if you need to record that, guys. Lastly, for resistance, again, here it is. What is resistance? There it is in the box. Don't forget to think about the symbols and the units. All right, guys, that's it. In the next lesson, we will be moving on to talking about how do we properly draw electric circuits. So we're going to have to learn about some of the symbols that the different devices have. Every circuit is going to have a power supply. It's going to have some wires and it's going to have some devices. So we need to learn how to properly draw them things to make it easier for us to draw diagrams. So with that, I hope to see you all well in the next lesson. So guys, if you give the video a like, it will just help other students who might be having a hard time with this stuff to find it as well. It just makes us rank higher on YouTube and it just helps us help more people. Okay, consider subscribing to the channel as well. It will help you find the videos and see any notifications when I post new ones. So I'll see you in the next video, guys.